In the world of remote sensing, high-quality satellite imagery is no longer a luxury, it's essential. From monitoring crop health and urban development to tracking environmental changes like deforestation and glacial retreat, the demand for sharp, spectrally accurate images has never been higher. But here's the problem. Satellites face a fundamental trade-off. To capture rich spectral information, what materials are present, their chemical composition, you need low spatial resolution. To get fine spatial detail, crisp edges, clear building outlines, you sacrifice spectral fidelity. This is where pan-sharpening comes in. Pan-sharpening fuses two complementary data streams: a high-resolution panchromatic pan image, which captures fine spatial details but lacks color, and a low-resolution multispectral MS image, which holds rich spectral information but appears blurry. The goal? To generate a single high-resolution multispectral HRMS image that combines the best of both. For decades, this task relied on handcrafted methods like component substitution and multi-resolution analysis. They were interpretable and efficient, but limited in their ability to model complex, nonlinear relationships between the two modalities. Then came deep learning. Early deep learning models like PNN introduced simple CNNs that dramatically improved results. But even these were constrained by static fusion strategies, mostly channel concatenation, lacking the adaptability to handle diverse spatial and spectral variations. Next came transformers. Models like Panformer and CMINet used cross-attention to enable global interactions. But they had their own problems: quadratic computational complexity, one-way information flow, and a tendency to smooth out high-frequency details. Worse, they often failed to preserve fine-grained correspondences. Recently, a new paradigm has emerged: in-context conditioning, popularized by architectures like MMMamba. Instead of relying on fixed fusion modules, it concatenates all modalities into a unified sequence, then processes them jointly with self-attention. This enables deep, bidirectional interactions across all tokens, ideal for multimodal fusion. But here's the catch: applying transformers directly to image fusion is computationally prohibitive. The self-attention mechanism scales quadratically with sequence length, making it impractical for high-resolution images. So what's the solution? Enter MMMamba, a novel cross-modal in-context fusion framework for pan-sharpening, built on the Mamba architecture. Mamba, a state space model, achieves linear computational complexity while capturing long-range dependencies. Unlike transformers, it doesn't rely on attention weights. Instead, it uses selective state spaces to dynamically modulate information flow, efficient, scalable, and powerful. But we didn't stop there. To fully unlock the potential of in-context conditioning and pan-sharpening, we designed a novel multimodal interleaved MI scanning mechanism. Here's how it works. First, we extract shallow features from both the pan and MS images using gated convolutional encoders. Then we apply layer normalization and linear projection, standard preprocessing steps. Next comes the key innovation: tokenization and interleaving. We divide the feature maps into non-overlapping patches. But instead of processing them separately, we interleave corresponding pan and MS patches spatially, creating fused sequences where tokens from both modalities are adjacent. And we do this in 4 predefined directions: left to right and up to down, and left to right to left, and down to up, and right to left. Why 4? Because real-world images are 2D. A single scanning direction misses critical contextual cues. By scanning in multiple directions, we allow the model to build a more robust, holistic understanding of spatial structure. Now, within each direction, we split the interleaved sequence into 2 parts, each representing a modality's contribution, and apply selective scanning. Here's the magic: we alternate between scanning one part and the other, not in isolation, but in a cross-modal alternating fashion. This ensures that information flows bidirectionally. Pan informs MS, and MS informs pan throughout the entire sequence. This is not just a technical tweak. It's a fundamental shift in how modalities interact. The output of this MISSM is then combined with the original projected features via element-wise multiplication and summation, preserving both the original signal and the enriched cross-modal context. After multiple layers of this process, we pass the final fused features through a convolutional decoder, add them back to the upsampled low-resolution MS image, and produce the final high-resolution multispectral output. But here's the real breakthrough: zero-shot task generalization. MMMamba was trained only on pan-sharpening. Yet when we feed it only the MS image, dropping the pan modality entirely, it performs image super-resolution without any retraining or fine-tuning. How? Because the in-context fusion mechanism is inherently flexible. By simply omitting one input, the model adapts to the new task. The same architecture, same parameters, just a different input configuration. This is unprecedented. Most models are task-specific. MMMamba is task-agnostic by design. And the results speak for themselves. On 3 major benchmarks, WorldView-II, GAUFEN2, and WorldView-III, MMMamba consistently outperforms all existing state-of-the-art methods. It leads in PSNR, SSIM, SAM, and ERGAS, with gains of up to 0.61 dB over the previous best. Visually, the difference is striking. Our method produces sharper edges, more accurate spectral details, and lower residual errors, meaning the reconstructed image is far closer to the ground truth. even in real-world full-resolution settings, where ground truth is unavailable. MMMamba outperforms all competitors on no-reference metrics like d-lambda, ds, and QNR, proving its strong generalization ability. And in zero-shot super-resolution, we beat not only deep learning models like SFI-net and pan-Mamba, but even traditional bicubic interpolation. Our PSNR reaches 36.49 dB, SSIM 0.9114, SAM 0.0299, and ERGAS 1.5515, top-tier performance across the board. To validate our design choices, we conducted extensive ablation studies. Removing the Mamba operator and replacing it with a self-attention block, matched for computational cost, led to a drop in PSNR. Why? Because attention is inefficient at scale. Mamba's linear complexity is key. Replacing in-context fusion with naive channel concatenation. PSNR dropped to 41.28 dB. Why? Because static concatenation fails to enable dynamic, adaptive interaction. Switching from interleaved to sequential token concatenation. Performance collapsed to 36.47 dB. The spatial adjacency of corresponding pan and MS tokens is crucial. Without it, information decays over long sequences. And when we compared multi-directional scanning to single-direction or global scanning, the multi-directional approach won consistently. It captures richer contextual cues. Even the local window scan, our modification to inject inductive bias of locality, improved performance over global scanning. Computationally, MMMamba is efficient. At just 5.06 G flops and 0.245 million parameters, it's lightweight and scalable, ideal for real-time applications. So what makes MMMamba special? First, it's the first to explore in-context conditioning in pan-sharpening, enabling deep, bidirectional unified processing of multimodal tokens. Second, the multimodal interleaved scanning mechanism, a novel architecture that ensures effective, spatially aware cross-modal exchange. Third, zero-shot generalization. Trained on one task, it seamlessly adapts to another without retraining. And fourth, linear complexity, making it practical for high-resolution, real-world deployment. This isn't just another incremental improvement. MMMamba redefines how we think about cross-modal fusion. It's not about forcing one modality to conform to another. It's about enabling them to collaborate dynamically and efficiently through a unified, intelligent sequence model. As remote sensing moves toward higher resolution, multi-sensor fusion, and real-time analysis, frameworks like MMMamba are no longer optional, they're essential. If you're working in satellite imaging, medical imaging, or any domain that deals with multimodal data, this is a paradigm shift worth paying attention to. And if you want to dive deeper, check out the code, the paper, and the full technical details on GitHub. Because the future of multimodal fusion isn't just about better models. It's about smarter, more flexible, and more efficient ways of bringing different worlds together. Thank you for watching. Stay curious, and keep pushing the boundaries of what's possible.